Well, there you go.
Yeah, that's it.
Okay. Yeah, hands in there. Thank you, mate. Here's a great. As the good Herbert.
So you've got 3 improvement sites.
Okay,
Okay, I think
let's
we're
not make
ready.
any more changes.
I think we're ready to roll. Good morning to day 3 of Condensed Matter in the City. I'm glad that you managed to find your way here. Of course, those who aren't, yes, are probably still looking. We're delighted this morning to make a shift into neutral territory, mainly the physics of spins. And Seamus is going to tell us about a new methodology he's been developing, which involves witness spins that give signs of spin-ons in this Herbertsmithite. So we're really looking forward to it. Normal story, 1 hour, 20 minutes. If you can end 10 minutes before the end, but we're going to interrupt like crazy, as you know.
Yes, please. Thanks for the introduction.
Yeah.
There's a lot of strange new stuff in this talk, both technology and physics. So it'd be much better if you just interrupt me as we go along. All right, so it's my privilege to represent this team. The theory lead is Felix Flicker at Bristol, and Ian Wootanen is the key.
The mic isn't picking up the sound properly. There's a lot of mumbling. Probably have to go closer. Right.
Well, no,
It's connected.
Start talking.
start talking.
Yeah.
I'm talking. Okay, it says I'm talking.
Yes.
It says talking. It's called artificial intelligence.
Better now.
Maybe you could turn up the volume because the volume bar is pretty. Zoom controls for the microphone.
Volume's on max.
But I think Zoom has its own controls.
Well, that's.
Or maybe you might be better off just pulling the microphone out.
It's okay.
Yeah, all right.
It's fine.
Let's
Go
keep
for it.
going. Okay, so the theory team, so Ian Wootanen, he's here today. And on the experimental side, Hiroto Takahashi and Jack Murphy. And Hiroto is here as well. So if I hope you have many questions about this project, and if you do, ask these 2 colleagues because they would be delighted to tell you about it. All right, so quantum spin liquid is a hypothetical state of matter. I hope no one takes that personally. But for example, here is this beautiful review paper by Broholm and all these superstar colleagues, and they say, I'm like in the second sentence, although there is not yet universally accepted experimental evidence that establishes that any material has a spin liquid ground state. So, if you don't read the rest of the sentence, you can deduce that we don't have any spin liquids. Which are guaranteed. Now, there's a variety of possible candidate materials. And those of a certain generation, remember when Phil Anderson proposed that the next frontier of quantum matter research would be to find RVB and quantum spin liquids. And some people in the audience, I won't name names, have been working on that now for many decades. So we have different types of candidate materials. The most mathematically beautiful one is the Ketiev XYZ model on the honeycomb. It's just so beautifully elegant. But there are almost no materials whose real Hamiltonian can be like this. It doesn't matter what your theory colleagues tell you. There's always higher order terms in the exchange. Then you have fairly complex and exotic ones that I'm not going to discuss. But there's lots of Kagome materials, which spin a half. And they're really excellent candidates. They're lovely materials and they're excellent candidates to support a quantum spin. Then, I didn't write this. The Broholm and colleagues wrote this. So they say that there's little or no doubt now that quantum spin liquids exist in theory, but do they exist in fact? And In one dimension, there's tons of evidence, but much of the exotic physics can't exist in one dimension. But beyond one dimension, there really is no certainly demonstrated material, whose ground state is a quantum spin liquid. Now, people move the goalpost. You have people who say, well, the phenomena at 10 Kelvin are maybe paramagnetic when they should be antiferromagnetic, and therefore it's probably a quantum spin liquid. But that's not really a logical argument. The quantum spin liquid is supposed to be the ground state at 0 temperature. Okay. You can read the literature. I won't belabor this anymore. For a newcomer like me, the question is, do these things exist? And if they do, how can you prove that they exist as an experimentalist? Now, in the last few years, there's been a theoretical breakout in this business. So Amir is one of the leaders. Also, my colleague Steve Blundell, also Eugene Demler, Patrick Lee, Bert Halperin. This is a very serious business. People began to realize that even if you have a material which forms a quantum mechanically disordered state with 0 magnetization, which is what the quantum spin liquid should be, still there would be noise. Okay, in different models, there would be different types of spin noise, which should emerge and allow you to identify and fingerprint which spin liquid you have. So instead of writing a paper saying, no order is detected at any temperature, therefore I think it's a quantum spin liquid, you could imagine writing a paper saying, the fingerprint for U1 Dirac is the following in terms of the noise. Here's the measured noise spectrum. The state is identified. That's what we like to achieve. Many ingenious ideas in these papers. All right, now let's turn to Herbertsmithite. So Herbertsmithite is about the most famous candidate quantum spin liquid. It's got an almost perfect Kagome lattice with very, very little off stoichiometry in the plane, in the Kagome plane. It's almost perfect. You can tell that from NMR. Like Iman's beautiful paper showed that. If you look down on the Herbertsmithite Kagome plane, so here's the Kagome lattice. And there's a copper. These blue guys are coppers. And they're spin a half. They're 2 plus spin a half. That's known with great confidence. There's 2 other species in here. So there are zinc 2 pluses at 3 of these sites. Let's say an ordered one. Here, there's 3 zincs. And then there are chlorine ions. There's 3 chlorine ions. That would be a perfect crystal. It's known from the susceptibility at quite high temperatures. That, from the Curie-Weiss susceptibility, let's say at 100 Kelvin, that the antiferromagnetic exchange interaction strength between this spin and that spin is like minus 200 Kelvin. It's huge. Okay, and as I'll show you in a second, it's also known if you cool down to 50 millikelvin, it doesn't turn into a ferromagnet or an antiferromagnet. It just remains in an unidentified state. Okay, so it's a beautiful material too. If you ever get to see the crystals, they're absolutely lovely. So let's think of this like as the hydrogen atom of quantum spin liquids, a prototypical compound, where if the theories are correct, there definitely is quantum spin. We can't prove that in reality. I can't. All right, now, so that's what I just said. Quantum spin liquid is widely viewed as the theoretical ground state of this set of spin halves on the Kagome lattice. Now, experimentally, yeah.
Here's a question. The zinc and chlorine atoms, because they are different, that will make the crystal fields. This model doesn't have C6 symmetry, it has C3 symmetry, right?
Somewhere above and below the plane, so it still preserves the correct symmetry. I just looked down from the top. I'll show you a 3D picture.
Thank you.
Okay, so here is electronic specific heat. And this symbol here is 0 Tesla. So, you know, once you start going to finite magnetic field, depending on what the magnetic state in the system is, you can start occupying those states or altering the available states at finite field. So just look at 0 field. So at 0 field, the electronic specific heat comes down, 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 down. And down here, you know, maybe 0.3 Kelvin or something, it collapses. And then nothing, there is no phase transitions detected down to lower temperatures. You can measure the susceptibility using conventional techniques, which I'll talk about later, or by site-specific susceptibility, like IMIDA is using NMR. And what you find is that the plane, the susceptibility of these spins in the plane remains constant. And then around 30 Kelvin, it drops precipitously. So for a very long time, people have regarded that drop as the formation of the singlets from the free spins, and then possibly their condensation and entanglement into a quantum spin liquid. But certainly the susceptibility is the night shift actually, but the susceptibility of the spins in the Kagome plate disappears below around 30 Kelvin. Those of you familiar with the cuprates, God forbid, but the same thing happens. The same thing happens in the cuprates in the pseudo-gap phase, right? And that's one reason why Phil thought it was a quantum spin liquid.
Is the specific heat linear at low temperatures?
It's not. Ask me that question again later in the talk when I show you what happens at low temperatures. Okay, it's a very good question. And the caveat I gave about fields is important. The phenomena that occur in this compound with different fields are very different. Yes.
Seamus, just to say, there is an inset in the top left.
Yeah.
That does seem to show it's linear.
Yeah, well, I was trying to avoid commenting on that. Yeah.
Just in the middle plot, what's being measured there?
So they're measuring the night shift, but you see the one that says grid, you can measure the component of the susceptibility.
The night shift of what?
The night shift of. Yeah, I don't remember. I'd have to read this paper again to remember which one it is. But they have several important papers saying that they can distinguish the susceptibility in the plane from the susceptibility out of the plane by having sensitivity to ions at different locations in the crystal. But there is a very large susceptibility, DC susceptibility. And that's been known right from the beginning. That's been known for over 30 years. And we'll see where that's coming from in a second. And people have known very well where it's coming from. We didn't find that. Now, when you do neutron scattering, you know, at decent energies, at 1 Kelvin, 10 Kelvin, 50 Kelvin, and so on, there's very little structure there. There's certainly no antiferromagnetism there. There's no dispersing spin waves. There's no sharp spots. There's just this diffuse stuff. And of course, people take that as evidence that in a fairly complicated argument to me, but anyway, they take that as evidence that it is a quantum spin liquid, because if it has fractionalized excitations, which are spin-ons, they could be beautifully ordered. They could have a lovely band structure. But we don't have any spin-on accelerator with which we can shoot spin-ons at the spin-ons and do a successful scattering experiment. We have to shoot a different particle which isn't fractionalized, and that really makes diagnosing these materials very complicated. Now, in between the layers, in between the Kagome layer and the next Kagome layer above, there's a layer of zinc atoms, zinc ions, zinc 2+, which are spinless. Okay, and if this layer and that layer were perfect, then the material would basically be perfect. All the DC susceptibility at low temperatures would disappear, all the weird neutron signals would disappear. And for at least 25 years, people have known that this layer and this layer are disordered, in the sense that there are some copper atoms substituted on the zinc sites. And depending on who grows the crystals and how they evaluate them, they report numbers, let's say between 10% and 30% of the copper sites, of the zinc sites, have copper atoms on them. And in this cartoon, the copper spin half substitutional ions are just shown as these blue guys in the zinc. Now, while you're picturing this in your mind, at the same time, everyone imagines that there's a quantum spin liquid in the sheet in between. So you have a quantum spin liquid, and then you have a layer of spin half ions, but at disordered locations, one on top and one on the bottom. That's the picture to keep in mind. People have hated these things for decades. They just mess up all kinds of traditional methods of understanding this material. For example, if you cool down, you'll find out that the Curie-Weiss susceptibility is about 1.1 Kelvin. You cool way down, far below 1 Kelvin. Well, approaching 1 Kelvin and going below it, you'll find that there's a Curie-Weiss susceptibility. Now, but the Curie-Weiss susceptibility of the spin liquid was 200 Kelvin. So there's some other spin degree of freedom, which is beginning to interact in an antiferromagnetic fashion, because Curie-Weiss temperature is negative, but in a very weak fashion, with interaction strength 1 Kelvin. If you do neutron scattering down to the lowest energies, which were achievable in those days, nowadays it probably could do better, but if you do neutron scattering, there's a ring of neutron scattering, as if you have a disordered environment of spin halves. And they can tell from from scattering in different crystal directions that this is interlayer interactions. So it's interaction of one of these guys, let's say, with one of those guys through the spin liquid. And furthermore, you can tell that it's antiferromagnetic. That's been known for a decade. Yes.
So that Curie-Weiss theta is of the spin population of the copper impurity.
Yes.
It's not like there's any Curie-Weiss action in the Kagome.
So everyone's working assumption has been that it's the copper with the spins, right? And in our own calibration, in the Rotose calibration, of the Curie-Weiss as we can measure it for the samples where we think we know the density of these guys. Yeah. It makes sense. Okay. Comes out quantitatively.
So what's the density of the interstitials, and how large is the sample variation?
So there are no interstitials. There are
intersubstitutions.
Substitutions.
Yes.
Right. So in our samples, about 30% of these zinc sites are occupied. Are occupied by coppers, but these crystals can be made with a variety of occupations of these sites. And in fact, right now we're involved in spanning part of that range to see what happens. Yeah.
Just to ask, so is this substitution sort of in the sense that also the copper sites are occupied by zinc because they're actually extra copper?
Okay, great question. So I find myself not, even though I've read and discussed and thought and talked a great deal about that question, I find myself not competent to answer it, because the people who measure the copper substituted on zinc site intensity often don't measure what's the resubstitution on the other site. And so there is some discrepancy between the reports of whether it's pure intersubstitution or whether it's off stoichiometry, which is doing this, okay? And I'm just not expert enough to know the answer. We can find how many spins are on the zinc sites, but literally that's all what we know. Yeah, there's a large out of plane signal. So whatever's happening, the spins are communicating through the quantum spin liquid. All right. So, following Felix Flicker here, so we wanted to take a different point of view. And of course, you know, STM people love impurities. If you don't have any impurities in your STM experiment, you don't have any signal. So we're not terrified by them. We like them. They're our friends, right? So we wanted to think of these guys no longer as, you know, impurities destructive to our understanding of the material, but instead to think of them as quantum mechanical witnesses to be used to get information from the quantum spin liquid, with which they must be interacting. This was Felix's idea. Okay, that's the strategy. Yeah.
Should we think of your 1 Kelvin as the residual interaction between the witness spins themselves, or should we think of it as the strength of the interaction with the layer?
Okay, great question. So Felix and I were, shall we say, going back and forth. When I'm working, I'm sometimes rather abrupt. So we were going back and forth on this. Where does this number, why does this number come from? And one morning we were at a meeting in Amsterdam. We had an hour together in the blackboard. We just fought it out. And we basically understand where this number comes from. And I will show you in about 10 minutes.
Okay.
All right. So here's the plan. Exploit witness spins and their dynamics, not just their existence, but how do they, time and energy dependence of what they're doing. How does it, what information does it give us about the putative quantum spin liquid? Okay. Spin noise spectroscopy. All right, imagine you're an experimentalist and you're measuring a signal and there's some noise on it. That's where the experimentalist should laugh, right? Because all signals have noise. Okay, you can subtract the average, and that'll give you the noise signal. The variance of this thing is just the average of it squared. Correlation function is your product integrated over time. If it's, you know, Gaussian, fluctuations, if the bath of fluctuations can be represented as Gaussian, then the correlation function will have a characteristic relaxation time. And the noise spectral density is the Fourier transform of the noise signal, modulus squared, that's the power at a given frequency in the noise. And this is the equation experimentalists use. We can't take t to infinity, but in fact, we often take t up to a day in order to get the whole thing. Okay, so that's just a generic statement about noise. And by the way, if you think you don't like noise, I mean, the whole cosmic microwave background radiation story for the last 30 years, plus all the Nobel Prizes and everything, it's all noise. That's all it is, noise. Okay, so we're going to measure magnetization noise. Here's actually a piece of Herbertsmithite. Yeah.
I've been kind of studying noise experiments now, and we're just trying to differentiate whether it's Nyquist noise or, you know,
Yeah.
or pure shot noise.
Yeah.
And the hard part is differentiating. So how do you know what kind of noise you have, even in magnetization?
So if you, okay, if we have a conductor, or, yeah, so if we're dealing with a situation where there are particles of conserved charge and they can move, then you know better than me, it's a very difficult situation, because you have multiple different sources all in the noise. If you're dealing with an insulator, and you're dealing with one type of spin at one site, then you can represent the dynamics of that object by some kind of either Lamore type representation with a lifetime, and then sum over the ensemble. Or you could use a stochastic dynamics equation to try and simulate what's going on. Those theories usually have only 2 or 3 parameters in. From the noise spectrum, if you have an adequate model, you can fit the parameters and satisfy your copies. That's how we do it. Okay. All right. All right, now we're going to measure noise coming from a piece of Herbertsmithite. And anyone who has the courage to go to my lecture this evening, I will discuss this in more detail in other materials, a bigger picture of what this means. But here, this is Herbertsmithite. We're going to measure magnetization noise in Herbertsmithite. Okay. Now, so we use a squid. It's a commercial. We use a couple of different types of commercial squids depending on what we're trying to achieve. It's got a superconducting pickup loop. This is a closed superconducting circuit. The sample is in one side. If the magnetization of the sample changes, the flux threading this loop changes, but the total flux is conserved, so some current is sent over here, which is detected by the squid. Very conventional set of ideas, which has been used now since the early 1960s. So we have several of these machines now which are dedicated to this type of correlated spin noise spectroscopy. They have the same strategy, but engineering, they're really quite different. They are not your father's squid susceptimeter. They're really quite different. So typically we can get femtotesla per root hertz sensitivity, and in a bandwidth now which is between 8 and 9 orders of magnitude wide. So we can get a really wide range of so for neutron scattering colleagues, so the energy resolution is a femtoelectron. So you can go places where you can't go with a scattering experiment. And with modern technology, we have this information in real time. In the old days, you had to square the signal, integrate it up, plot it on the screen, and that's your power spectral density. But nowadays, you can take that at 10 gigahertz. I mean, that's how people spy on your telephone. So we take data with microsecond resolution to see what's happening inside one of these samples. Okay. Oh yeah, right. So there's a graph from a spiral spin liquid. The noise floor is down here, John. And it's about 8 orders of magnitude. What I saw plotting last week. Yeah.
Seamus, what would be what would the signal be for just a garden variety anti-fermat?
So all ordered states that we're familiar with. Once you go through the classical phase transition into the ordered state, the noise would disappear very rapidly.
Even for an anti-ferromagnet?
Well, it depends on the spectrum of excitations, but it should disappear rapidly, like the density of states.
Because we know it's not the true ground state.
Well, and if it's an antiferromagnet, you do know that it's the ground state.
Oh, okay. But
Right? If you've already had the phase transition.
Yes.
Right. And if it's a paramagnet, there's always a little bit of paramagnetic noise, but nothing to worry about.
Okay.
Now, to cool the samples down, Laura, we have to put a silver wire from the dilution fridge down into the squid and bring it right up next to the sample. That's the only way to get enough thermal conductivity inside the apparatus to get the sample to be cold. So that's great, but there's noise coming from the Fermi surface of the silver. You can see the noise of the electrons at the Fermi surface of the silver. So there's a lot of tricky stuff. If you want to read more about this technology, it's in these papers by Hiroto, Ritika Dusad, so Cox. Yeah.
So coming back to the question about electromagnet, say it's a density of 8 times the linear.
Okay.
Yeah, what's the reference for? Yeah.
Okay, so the truth is, I haven't bothered to study any ordered states because the statistical physics of those states is very simple. Okay, and the noise is the same as the specific heat. So, you know, as long as you don't have some weird correlation, nothing strange. Now, there is a case where something does happen, which is if there are domains in a ferromagnet whose pinning is weak, right? Okay, then they can flicker around. That's called Barkhausen noise. That's been known for 100 years. Okay, so we stay as far away from ferromagnets as we possibly can.
Do you expect the noise to be different? I mean, depending on different sort of field dependence of the anti-ferromagnetic correlations?
I didn't know we were going to discuss these subjects. Okay.
Because I mean,
Yeah. No. Great question. So,
What was the question?
so how would the spectrum of the noise be associated with different states? I think that's
basically, I mean, because the anti-ferromagnet will have a field dependence, right? It's
That's
different
correct.
between quantum spin liquid and a simple anti-ferromagnet.
anyway. You know, if it's non-interacting undergraduate statistical physics, the specific heat and the noise are the same. So you would know at least. But in general, lots of complicated cases have been considered not. Fermi liquids, quantum spin liquids, all kinds of cases which have different band structures for their real or fractionalized excitations. And those bands and the noise is said to be able to distinguish which one is which, right, according to these theories. Yes.
So in 1D, I can solve exactly quantum.
That's correct,
right?
correct.
So I can solve this problem in 1D.
Yes.
As quantum different from, an inductor magnet. I can really make it one magnet.
Completely agree with that. Our boss, actually, Hideki Tagaki, would like us to do one-dimensional spin noise spectroscopy. However, these experiments are not cheap, and we already know how one-dimensional systems work. So experimentalists don't get rewarded for it. Sorry. All right, let's go back to Herbertsmithite.
Question, how does this
Yeah.
avoid the fate of the fluctuation dissipation theorems? Because ultimately, if that holds, you're just measuring a T times chi double prime over omega.
Super question. See this paper here, Pierce?
Yeah,
2408-00460.
okay, I know it well.
Read it. It shows how the fluctuation dissipation fails at a particular frequency and temperature, and it shows how the noise continues to evolve after that point.
So this is beyond
Absolutely.
dissipation.
The idea that fluctuation dissipation is guaranteed to survive at low temperatures in a strongly correlated material is not.
Okay,
Right,
right.
that's it.
All right, very good.
You actually have to measure the noise.
Yeah.
Okay. All right, great. Oh, yeah, okay, so there's our toys. So we have developed a bunch of new technology now to do this. No one can afford liquid helium, especially in the UK. So we're using a cry-free refrigerator, but it's ultra low vibration, one of our design. And then we use millikelvin vibration isolation system, also of our design. It's 2 stages job. And then we use, there's multiple mu metal and niobium shields to shield the sample. We can get down near 10 to minus 15 Tesla sensitivity. And if you're willing to average for a day, we can get well below that. And the ambient field is around 10 to the minus 9 Tesla. So this is different than a conventional device. Okay, and now why am I belaboring this point? Well, I want to tell you something interesting. The magnetization, the magnetic field noise in this room is very loud. It wouldn't have been loud 25 or 30 years ago. It would have been modest. It would have been from the power supplies and so on. But now it's very, very loud, and it's coming from all of you. And the reason why it's coming from you is that you have a mobile phone probably in your pocket or in your backpack. And these things have high field magnets inside. And when you're walking around, the fringe field from this guy is being detected by your ultra-sensitive device. So the screening for this was very hard to achieve. All right. Okay. So we have been developing this idea now for a while. We started with dysprosium titanate, the monopole fluid material. I'm going to talk about this evening. And that's a high spin. It's basically classical spin with a few little quantum mechanical quirks. Then we went to this one, spin 3/2. This calcium chromate compound. We learned a lot from this. It was a very challenging experiment, but we learned a lot. And now we try to go to spin 1/2. The coppers on the zinc sites of Herbertsmithite. The magnitude of the signals you're dealing with is going down steadily. Even if the density of the number of spins you're dealing with is more or less constant from sample to sample, of course, the signal is going down with the size of the moment, right? So we were anticipating that it would be sub-picotesla for Herbertsmithite. Okay, Herbertsmithite. Okay. These samples are about 5 or 6 millimeters long and about 1 millimeter wide. And they're cut from a somewhat disordered wood, but they're reasonably simple.
What's the purpose of
Wow, this is like an exam. If you want to measure the fluctuation dissipation theorem simultaneous with the noise, you have to have the drive. And if you don't want to have unknown constants between the device you're using to measure the susceptibility and the device you're using to measure the noise, you should put the drive curve for the susceptibility into the same apparatus, which is detecting the noise. And the second counterwound coil here is to keep the primary field from the drive coil out of the noise channel. And again, if you do the numbers, you'll find out that that's quite difficult to do. Okay, great question. Okay. Okay, I have to play some sound. So now I'm making this sound simple. This is Hiroto's DPhil work at Oxford, taking about 3 years, but we can show you the result in about 3 minutes. So that's the way science works. Let's see if this works. Here's the table. Let's do that again. There'll be an exam after I play this a second. The bottom one is the magnitude of the flux signals in the history. What's happening is a very large energy events. Okay. So that's what a raw data set looks like now, except with our devices, it's enormously bigger. If you're taking that at megahertz and you're measuring for days, you end up with giant data sets. But that's the modern world. Okay, so here's what I just showed you. If I show, here's temperature of that sample. And here's the detected signal, the flux coming from this object, squared in milliflux quanta squared. So you start at high temperature. This is the electronic background noise of the squid. As you're going down, maybe it starts to change a little bit, but then when you approach 300 millikelvin, you start to see a lot of action. 250, you see very large noise, 200, and 150, it starts to fade away. By the time you get back to 50 millikelvin, you're back mostly to the electronic noise. So yeah, so these were the histograms of the magnitude of the various events. And now you can always quibble about what's an event, right? It's in noise. How do you know whether one peak is a real event and another peak is not a real event? So you have to, there's some arbitrariness in choice of the magnitude of the event, but we were fairly level-headed about it. This really is what's happening. You have electronic noise and then you approach a lower temperature and it blows up and then it collapses again. So here's the measured power spectral density of that noise versus angular frequency on this axis and temperature on that axis. And the power spectral density is basically scale invariant. It doesn't have, we don't find the characteristic relaxation time anywhere in this temperature range. The magnitude of the noise, well, this is squared, so it's a few, the bottom is a few tens of femtotesla and the top is 10,000 times more. both from the DC susceptibility and from the variance, you can figure out how many spin halves are producing this noise. And they are in very good agreement with the number of spins, which are the copper spins substituted on the zinc sides at 30%.
Seamus?
Yeah.
Sorry, maybe a naive question for non-experimentalists, but what you see is sort of this 1 over omega.
Yeah.
Now this 1 over F noise, right?
Yeah.
It's well known, it occurs everywhere. It's in our power supply wires.
Yeah.
How do you know that what you're measuring?
Well, because it doesn't occur everywhere. It's non-existent above 300 millikelvin, and if you go 300 up, it's not there.
Wait, but you showed it very explored. I said for any function you show, there's 1 over F component present.
Well, this one is cut off just a little bit above 300. This is a better way of looking at it. And if I expanded this upwards, their only background noise is the electronic noise from the squid, which we can calibrate in. So this noise isn't everywhere, and it isn't there at all times. It appears exactly at about 350 millikelvin, and it grows rapidly. And you heard that for yourself. The white noise wasn't there the whole time. It appeared suddenly. Okay. So this is the color code of the power spectral density, again, versus angular frequency. Oh yeah, we didn't shift the frequency. That was the real frequency at which the noise is coming from Herbertsmithite. Right.
I'm a little bit confused. You're saying that you only detect the copper speed noise here, but not the speed noise from the Kagome plane at all.
We don't, yeah, so we have the magnitude of the signal we can detect is consistent with the copper atoms on the zinc sites. Plus the table.
But the switch should be picking up all speed noise, right?
Fine, but suppose it's a real quantum spin liquid, which is just a superposition of singlets. They all have no magnetic pole and they generate no noise. So you have to.
The speed noise, but not the same.
Well, nobody knows. We can go back to those theory papers, and some of them argue that the spin-ons will produce spin noise and others don't. But the spin noise, in that case, will occur at the Fermion of the spin from the and that energy is pretty high. And so the frequency is pretty high. So we can detect the noise coming from the metal quite easy. I was hoping we would detect the spin on the noise curve. We haven't detected. Great question. Yeah.
What happens if you factor out a cough, a fluctuation dissipation term, the cotangent of say, omega over 2t term? Do you see a temperature independent spectrum left over?
Factor out means subtract.
No, divide by.
Divide by.
Yes.
That's a great question. I don't know the answer to that. That's a very good question.
So does this noise linearly proportional to the number of impurities you have?
Absolutely. We can tell that from the susceptibility at higher temperature. I'll show you that in a second. Look at the power law. Let's come back. No. So the power law was not 1. The power law started off being, somewhere down near 0 for the electronic noise in the background. If it were white noise, it would be 0, right? So it comes up from the background as you're approaching this transition, which you guys all heard. I didn't fake it, you heard it yourselves. As you're approaching that transition, the power law grows, and when it passes through the transition, then it becomes 1 over F noise, but not before. So the 1 over F is a property of whatever state is appearing. It's not a property of the background. All right. Now, you can measure the total power in here by measuring the variance. Yeah.
What's the fastest change in manifestation you could detect?
Right, that's a tough question. So our acquisition system could detect a change down below a microsecond, but our fastest squid can't reach below 10 or 13 seconds. But the next generation squid will be able to get up below a microsecond. So in the future, the bandwidth of these machines should be from the tens of megahertz all the way down into the millihertz range. Should be enormously. And for phenomena occurring, like transitions occurring at low temperatures, because of the energy range that you're dealing with, that actually is the correct band in which to find out what's happening.
So you're operating the squid in flux sort of loop mode, and you've got a bandwidth that's a few hundred kilohertz.
That's correct.
Yeah.
Exactly. So we would like to change to an unlock matched to the other requirements. I would love to talk with you about that, John. The variance tells the total amount of power of this noise. So you start off up here, there's a little bit of power, it's the electronic noise of the squid. Then you start cooling down, and then you reach this transition point. That's, you all heard the maximum in the noise there. And then what happens is the noise collapses down again, we don't see any other phase transition. But we think this is a phase transition, and it's certainly one which has not been reported before in Herbertsmithite. In fact, no, we know it's a phase transition. If we go back to conventional concept for DC susceptibility, where you have this very small DC field and you measure the total flux, then we can measure the susceptibility. Coming down here, it's the Curie-Weiss law for the 33% of zinc sites with copper atoms. But as we approach 260 millikelvin, there's an extremely sharp cusp. And then the susceptibility drops way down again. We have repeated this on multiple samples. It's not a mistake. It's absolutely real. And this had not been seen before, even though susceptibilities have been measured for many decades. But the ambient field in our apparatus is very low. It's many orders of magnitude lower than conventional. Peter, how are you?
So could this simply be the establishment of correlation, along the C-axis of the
Yes,
activities?
absolutely. That's what's happening. Let's go ahead. That's Felix's job to answer that question. But okay, and there's an Edwards-Anderson order parameter. It's known from other techniques that there's no antiferromagnetism at low temperature in this compound, from scattering and from USR. So
there's a short-range correlation, right?
absolutely, but there's no long-range order. So if you take a spin glass order parameter from our data, it looks like this. This is the Edwards-Anderson spin glass order parameter. Why would we take that order? Yes, sir.
So on the subject of the fluctuation dissipation theorem, you can measure the susceptibility in driven mode, so you can measure the complex susceptibility. And you can show us that.
You have the fluctuation dissipation data for this compound.
Yes.
That was what that.
I think I confirmed at least some about 150 millikelvin.
So we have the whole thing. All right. I was driving home from work one day, having my colleagues explain all this stuff to me. Obviously, I didn't do this stuff. And I was thinking and thinking, what can this be? And I started, and there's a lot of literature saying that there's no exotic ground state in Herbertsmithite, blah, blah, blah. I started thinking maybe it's interaction-driven spin glass, which is being formed by these random spins, which are not in the Kagome there. So I wrote a note. I asked Jack Murphy and Hiroto, do the following experiment. Thermalize above any possible transition, come into equilibrium, then jump the temperature to a new temperature and measure the time dependence of the susceptibility. So, if you jump down from 400 to 350, or from 400 to 300, and this is a day, and you just measure the susceptibility for a day, nothing happens. But if you jump down below the transition I just showed you, which is at 260 millikelvin, and as soon as you do that, you get log T dependence of the susceptibility, which is the classic signature that you have to speak. So we then started immediately thinking that this is some kind of interaction generated spin glass, which is the real ground state of Herbertsmithite. But it's the witness spins, so it's a very strange state. It isn't actually all the spins in the Kagome there, it's these guys hanging around outside, which have become normal. Yes, sir.
Did you see that field pool and zero field pool difference?
Great question. Many people have asked us that. Having struggled for years to keep up with the DC magnetic field, we are not quite good for things. It's a very hard experiment for us to do. It's a great question, but it's very hard for us to do. Okay,
Can you
now,
do AC?
pardon?
Can you do AC?
Yeah, we have complete AC susceptibility now.
So the frequency dependent.
Yeah, no, we know that I should say it clearly, the fluctuation dissipation theorem, it appears to be maintained in this compound, down to the. Okay, now what does this all mean? All right, so this is over to Felix and Ian. So how would these guys? Now we know they communicate across the spin liquid. We know that from the neutron scan. And we know that the correlation is antiferromagnetic. And we know there's no long range. Those are facts. And the witness spins are pretty sparse. Quite a number of them have no nearest neighbor spins, and that is an important fact that is necessary for the final deductions. But exactly how would you communicate through a quantum spin liquid? Okay. Actually, there's little or no literature on that side. Okay, so here's Felix's idea. So first of all, you're going to consider every witness spin. I is witness spin site I, and J is witness spin site J, and we're going to not just consider nearest neighbors, but reach out for long distances to consider the interaction between every witness spin. Okay, there's spin a half, and obviously what we don't know is what is Jij, what is the interaction term through a quantum spin liquid. Okay, so the theory works like this. First of all, each witness spin is nearest neighbor to 3, and it's copper, and its 3 nearest neighbors are copper. They're all copper. So it has 3 nearest neighbors, and we don't allow in any quantum interference or anything in those 3 branches. We just add them together. And assign a coupling constant, gamma, to be determined later, for the strength of coupling between the witness and the quantum spin liquid. Now, Jij is the interaction, let's say, between this spin and that spin. Okay, but the interaction is occurring through the quantum spin liquid. So to get that information, we're summing over the 3 near sites here. We're summing over the 3 near sites there. And we're summing the susceptibility of the spin-ons of the quantum spin liquid at the distance between here and there. Okay, and do that for all pairs of distances.
But isn't there a problem with this idea of RKKY? Because the witness spins don't couple to the spin-ons like they would couple to conventional electrons, where you just get the second order RKKY, right? So here what you would expect is a coupling S dot S, where, right, and then S fractionalizes into emergent.
So in here is the fractionalized excitations.
But it fractionalizes into some gapless component.
That's correct.
And something gapped.
The solution here is fully gapped.
Or it doesn't fractionalize at all. You don't know.
Well, great question. Let's just look at the next page. Okay. All right.
I'm just saying you can't really say much about having, let's say, Dirac versus something else if everything becomes controlled from whatever gap you have.
Well, eventually you will. Eventually experimentalists will have these data for different gaps, for different types of spin liquids with some Dirac Fermi surface. Some Dirac, some with Fermi surface, some Z2 and so on. So maybe we can't do that now, but that's the plan. Yes.
Maybe you said this and I missed it, but what roughly the interaction, J, between the witness spins and in plate versus the one between
I'm next on the next page. I'm going to expand the definition of the term, which explains the interaction within the plate.
No, but I mean at a microscopic level, even forget about spin on Herbertsmithite surfaces or spin on bands.
Yeah.
Just J, about do the JS of S. The one within the plane 190.
Yeah.
But the one outside the plane is what?
So the one between the planes, its characteristic energy is 1 Kelvin. And that has been an outstanding mystery for 25 years. Because it should be 50 or 60 Kelvin. Because they're copper atoms, side by side.
Right.
So there is, but to solve this, you have to see the next page. Okay, all right, let's go there. Right, so if you want to find this function which communicates between the site above one witness spin, and let's say the site below another witness spin, through a quantum spin liquid. So you have to know what are the Green's functions for the fractionalized quasiparticles in that quantum spin liquid. And of course, to get that, you have to solve the Hamiltonian. So the Hamiltonian to be solved here is the Z2, is the gapped Z2 quantum spin liquid Hamiltonian mean field, which is widely believed to be the correct Hamiltonian for Kagome. When I first showed this data to Patrick Lee, I said, Patrick, please tell us what we should do here. I was talking about Kagome, and he said, well, it has to be a gapped solution, otherwise it doesn't make any sense. And that was 2 years ago, he was right. Okay, so you have a Hamiltonian for a Z2 quantum spin liquid. The fractionalized excitations are spin-ons, and they form some kind of a band. These are the Green's functions for the spin-ons in that band, and this is an integral over energy. So you're getting the susceptibility by integrating over the energy of all the spin-ons in the band.
But why are you buying into the religion of spin-ons?
It's
You're an experimentalist. You have to do the experiment and not make that assumption. But the theoretical idea that you're being inculcated with, right?
Oh, you'll be hard.
In the world, okay, in the real world, if you don't have a theory to be falsified, you can't publish. That isn't my fault, right? That's the way the world works.
Sure. If your goal is to check that theory,
I'm checking.
okay, but there should be, presumably you should have other candidate theories that you're going to contrast it with. Okay.
Yeah, we have half a dozen.
Okay.
After my last slide, ask me that question.
Okay.
I'll show you the
Right.
list. Okay. Go ahead.
But if there was a gap, you should see it in specific heat, but the specific heat just went to 100 millikelvin.
So the gap doesn't go to zero in the specific heat because it's only in the Kagome layer, and there's a whole bunch of other excitations outside the Kagome layer. That's exactly what confused the people in this field for 25 years.
So if you just back up a few steps in, did you say a moment ago that if there wasn't this spin liquid thing there, if you just thought about the layer of witness spins,
Yeah.
the effective J in that would be 50 Kelvin.
Yeah.
Should be 50 Kelvin. But so the argument is there must be something exotic that's happening because of this intervening layer to screw up the exchange that otherwise should be there in the witness
Correct.
layer. Is
Correct. That's
in
correct.
essence?
But I can start from another point of view, that I could have these molecules in 50 and
I'm just going to list the
see what happens in the plate. We have like
You can be.
three carbonates and one witness spin, and then we keep
Let
in glass inside.
let me step forward 2 more slides, okay? Just let's keep going. All right. Modulo Pierce advice, and what we call it criticism. The mean field Hamiltonian for Z2 quantum spin liquid on a Kagome lattice was worked out by Patrick Lee in this beautiful paper, and we just use that.
Mhm.
So why do we need to do anything? Because this is a theory paper, it doesn't have any real numbers in it, right? We actually have to put in J, you have to put in the correct unit cell dimension, and et cetera, to get out the answer. But it's mean field, and there are some constraints as well because of the fractionalization. There are some Lagrange multipliers that you have to satisfy, etc. So Ian and Felix worked all this out with the numbers for Herbertsmithite, with the quantitative numbers for Herbertsmithite. It gives T1 the hopping for an object of this geometry, 0.4 times JK, which is about 76 Kelvin. So this number is coming from susceptibility at high temperature. It's coming from the high temperature Curie-Weiss number. It's the Kagome spin-spin interaction strength. This number is coming from theory. It's the kind of it's the nearest neighbor hopping rate for the spin-ons if they exist. There is a band structure for these spin-ons. It's gapped. The gap 2 delta is about 30 Kelvin. We didn't force this to happen. 30 Kelvin is where the in-plane susceptibility collapses in Herbertsmithite. That's been known for 25 years. What we're purporting to measure, modulo Pier's advice, is the integral over those spin-offs, if they exist. All right,
What kind of what kind of pairing delta did you assume for this Kagome lattice to do this? I mean, you could choose extended S wave, D wave,
oh, it's S-wave, I think. Yeah,
extended.
I think so, yeah. We can ask Ian, but I think it is.
That's just the solution to some mean field.
Yeah, that's correct.
And that gap is for the symmetry of the lattice doesn't support the calculus.
And the quantitative values of the terms that go into the Herbertsmithite.
And how do you impose the constraint that there is 0 S wave pairing on site? That first constraint means that there's no on-site pairing. That's sort of lambda 1. Okay, so lambda 1 is doing your work here.
Yeah.
Mm.
This is Patrick's Hamiltonian, so has to be right.
No, right.
All right. Okay, so we can discuss with our theory friends in detail if you want. You know, having solved it though, we know what these excitations are. That means, you know, we can carry out this integral. That means we know this number for between any pair of sites. So if you're willing to subscribe to this working model, then we know that now.
What parameters did you come up with to do the fits?
So-
Delta and all the things.
Yeah. Well, so 2 delta is the solution produced T1 of 0.4 times JK, and it produced 2 delta of 30 Kelvin. But we didn't put those in, we just put in J and the lattice.
But why then was there a linear specific heat down to about 0.1 of a Kelvin?
Great question. That's a
It's
great.
inconsistent with this
that's-
model.
No, it's not, but it is consistent with our explanation of what happens in Herbertsmithite.
But if there's a gap of 30 Kelvin, how the hell do you get a linear specific heat?
Because the only thing that's gapped is the Kagome there. You have all this other action that I'm trying to reveal to you outside the Kagome.
But I thought neutron scattering sees the continuum is to much lower energies, right? I mean, the Nature paper of Yang Li.
Yeah.
I mean, it's not gapped that, you know.
Well, no, there's a controversy about that, yeah, of which I'm not competent to solve, right? Some people say this is gapped and some people say it's not gapped, and our result looks gapped, let's put it that way.
So you say if you make it ultra clean, ultra pure, then you would see the gap.
You should,
Specific.
absolutely, you should.
But then you should see a lot of sample dependence in the specific heat, right? So if you
Yep.
make your other samples which have less.
We're doing, so you can't, as far as I know, I'm not a material scientist, but as far as I know, you can't go to the pure point of this compound. But you can go in the other direction, which is what we're doing right now. All right, look at this story. So there is another constraint though. We know that the Curie-Weiss susceptibility is near 1 minus 1.1 Kelvin. So our simulation has to be consistent with that fact. To make it consistent with that fact, this number, the coupling constant, has to be 60 Kelvin. So that number is derived from the measured Curie-Weiss temperature, which we didn't measure, many people measured. This number is derived from the mean field solution. This number is squared because it's a 3-stage process, up, across, and up. And this is the nearest neighbor susceptibility, this number for nearest neighbors. And if you multiply those numbers together, you'll get 1.2 Kelvin. The reason why it has action at 1 Kelvin is it's a 3-stage spin process. From the witness spin, through the spin liquid, to the other ones.
So is Jij consistent with Yang Li's measurement of the CS correlation? Because the magnetic bandwidth of that will tell you, you know, what is the exchange coupling.
It is.
Oh, so it's
Yeah.
roughly 60 Kelvin.
Yeah.
That's pretty nice.
Now, here's the action. How much time do we have here?
We now have 20 minutes,
Okay.
including questions. So really 10 plus.
Now I have more questions.
Shouldn't that be dependent on concentration of the earthy?
This column here is measuring the dependence on the concentration of the impurities. That's the next stage of the.
But in the here,
Specifically to a lot of spin.
I have to explain to you how, where did all the noise come from? I haven't explained to you where the noise came from. So, let me do that first. All right. So this is a graph from Ian and Felix. Suppose you have a witness pin at this site in the crystal. It's at a zinc atom inside the small triangle below the surface. I suppose you want to understand how strong is the interaction with another witness spin. This is nothing, well, this isn't what's happening in the spin liquid. It's the interaction between this witness spin and, let's say, that witness spin, or this witness. It's a map of Jij for a spin-on band structure with these parameters. That's what it is. There's an analytic solution which looks like this. It decays exponentially because it's gapped. The rate at which it decays goes as 1 over delta, where delta is the gap in the spin-on spectrum. Makes very good sense. The range is a bit more, it's just slightly less than 2 unit cells, so it's long enough for things to be communicating. And if you go to very low temperatures, you can reach out quite a long distance, where KT is less than Gij. All right. Now, in a perfect world, you put one spin here and you put your sensor there and you measure the number and you're done. But we can't do that. We have a random ensemble of impurity spins. So now what Ian did is to do Monte Carlo. So we have a hypothesis. We have a quantitative map of what we think this function is. Okay, now to do the Monte Carlo, we have to make the witness spins into Ising spins. If you choose to criticize the project, fine. But it's very hard to do the Monte Carlo if you don't make this choice. It's really hard. So then we take a random distribution of configurable locations of the witness spins, taking this as given, run the Monte Carlo simulation and find out what happens to the magnetization as a function of time if the witness spins are interacting with each other through the quantum spin liquid, both time and temperature. So this is now simulation. So in simulation, you can calculate what's the magnetization of your simulated sample. And as you go down in temperature, these, large departures in the magnetization squared appear in the simulation, and then they disappear at the lowest temperatures. Here's the simulated histogram of magnetization noise. And let me go back again and just be very clear about this. At that point, there is only one pseudo-free parameter in the theory. It's the magnitude of gamma. Okay? And even that parameter isn't free. If you don't want to get the wrong Curie-Weiss number, you have to choose the correct value for that parameter. So if you were a hardcore experimentalist like me, you would say there's no free parameters. Okay, well, God heard that.
No.
No. It's on the screen here and here, but not here. Ah, this is off.
On the light bulb. Oh, you turn it off?
The green standby, isn't it? Doing fine on Zoom.
That's
How did you start the thing up there? It's gone to sleep is what it's done, I hope at least.
These screens you have it, right? So there are two screens. It must be the bulb.
the lights.
If the bulb goes.
One is live, it's wow, that's it.
No, that's not over.
Ah, all right, so let's continue.
Maybe we move out.
So the Monte Carlo simulation. The time sequence of the
I don't think they'll hear us.
And there is the result. It's high temperatures, there's no extraordinary note. Then somewhere a bit below 200 millikelvin, all this intense noise reappears.
I think it just I think it just slept.
You think?
Yeah. There was no loud sound.
Console.
It's the little remote somewhere.
Is there an on-off button for the beamer?
Well, we could switch the whole system off.
No, don't do that, don't do that.
I mean, this. Well, I can just see what happens if I.
Be careful for you.
Oh, yeah, so I switched the input to PC. It's flashing, but yeah, the light is on.
She was good after minutes.
Well, I think
We could go to question time.
Oh,
There you go.
Well done, thank you. What was
Turn it on and turn it off, right?
electrical engineering?
particular sequence.
All right, great, thank you very much, right? So here's the map of the simulated noise for Spinon-mediated witness spins. There's no noise, it appears suddenly, it grows to a maximum, and then it disappears. Here's the power law of the noise. It starts off at 0, it grows to the critical point, and then it turns into 1/f noise here. Here's the variance of the simulation. It grows from very low until it reaches critical temperature, and then it drops precipitously. And here's the predicted specific heat calculated from the model. It grows on the 33% zinc site substitution, and then it reaches a characteristic temperature and it drops precipitously. And of course, this is theory. The great thing about theory is you can calculate any order parameter you like. So if you calculate the antiferromagnetic order parameter from the simulation, there's no antiferromagnets. Whereas if you calculate the Edwards-Anderson glass order parameter, it grows. All right, so I don't have time to go through it now, but the same simulations can be used with some help from Mike Norman to calculate what's the low energy neutron scattering spectrum. And they also show the interplane antiferromagnetism that's detected in the original experiments. So the only thing which is not in perfect agreement here, and we didn't fake this thing, it just popped out, is that the characteristic temperature in the simulation is lower. It's near 150 millikelvin, whereas the characteristic temperature in the experiment is near 250. But aside from that, the whole phenomenology fits together very, very well, as does the Curie Weiss temperature, because we forced to fit the Curie Weiss. Right. So if you're willing to consider the possibility of spin-on mediation between quantum witness spins as a plausible theory, then what we have shown you here is that it's a doable technique. You can execute this technique. Just as you said earlier, now what we need to do is find out some other compounds and show that the same machinery would work for a different spin-on band structure, or a different Fermi surface or something like that.
There's also one general question. So you talk about witnesses and you take the idealized mean field Hamiltonian.
Yeah.
You look at the feedback, the mediated interaction between the witness spins, but you don't put the feedback of the witness spins into the Hamiltonian, right? So
I think that's a great question, and we have been considering higher order processes in the present models.
But it's not high order. There are just random fields coupling to the random magnetic fields coupling to the spin equation.
No, but in terms of calculation, they are higher order. You have
lower order than second order interaction.
I understand, but in terms of calculation, it's another round.
Oh, see, yes.
Yes.
I guess it's question time,
All right. What was I going to say? Thank you to my colleague.
Okay, lots of questions. Let's start with at the front. Okay, Andre.
Thanks. Seamus, so as you pointed out, the spin record is gap. When you model as gap, you will pretty common.
Yeah.
That is why it is consistent with what you said, that the interaction looks like exponentially suppressed. It should decay like that, right?
Yeah.
On the other hand, there is a direct dipole-dipole interaction, which is just a plain power law between witness spins. So why not ask the following question? Let's forget about the vegetable spin liquid, which is gapped anyway below 30 Kelvin, and ask how large would the interactions be
Yeah.
between those dipole dipoles.
So you can consider those in the model, it's doable, and Ian has done it, right? If you take direct nearest neighbor witness spin interactions, you will not get the same physics as observed in the experiment, because 10% of the spins are isolated, and their susceptibility will remain and grow on a Curie trajectory to zero temperature. So we ruled that out based on experiment.
I see, so you would claim 1 over.
Yeah, it's just not there. The susceptibility collapses once you enter the spin class phase. So you could take a next nearest neighbor model, but there is no, neutron scattering doesn't show any next nearest neighbor interaction, which is detectable. Okay.
But just the devil's advocate, I mean, the dipole dipole interactions are long range. You shouldn't limit yourself to just nearest neighbor, next nearest neighbor. They go forever as that 1 over R cube.
Fine, but for spin and a half at these distances, they're small.
Yes, that's true.
And secondly, they're primarily parametric. So
Right, but I was hoping that smallness is precisely what's going to give you 1 Kelvin. Okay, how about that? How about we take Occam razor?
yeah, okay. There's going to be a correction.
It's maybe dipole dipole interaction, like I think, and it was order of 10 millikelvin. So I think it was like we think this even nearest neighbor one is 10 millikelvin, and even the further one should be much smaller. And there's no way that can take the 2060 millikelvin partition. So that's why we think we can get at least a simple dipole dipole interaction.
So you're saying that if you just take the distance between them and compare the distance within the Kagome plane,
Right.
that's the difference between whatever 90 Kelvin kilowatts and what you're saying.
Right, and so yeah, because I think those 190 Kelvin, those large coupling come from the overlap. Anyway, so their exchange energy, not the simple electromagnetic field of the Yeah, so I think with the electromagnetic field of the dipole, the energy scale is at least like 2 over smaller than the observed transition temperature. So there's no way that can explain at least our experimental observation.
So no, let me answer one of your questions earlier. So we had considered nearest neighbor, next nearest neighbor, next nearest, and ferromagnetic and anti-ferromagnetic interactions, and plus a random singlet state, which is what Patrick told us should be there. But in the simulations, none of those things produce the suite of phenomena which are detected in the experiment. They're just not consistent with experimental facts. So although you can never rule out an alternative theory, right? Oftentimes your reviewers will ask you, have you ruled out all theories? That's a nonsense question. You can never rule out all theories, right? But we can rule these ones.
Okay, questions over there.
So I think what seems very convincing to me is that you have these spins on the outer plane basis, and there is some mediation of the interaction between those like through the tag right? And then because these things are arranged in a kind of random network, you end up with something. But I don't see what from your data like how you know that it's spin-ons doing. And there are some excitations in the Kagome plane. Somehow they mediate the interactions. Like, is that not equally consistent?
Yeah, completely agree. That's close to the point Pierce made earlier as well. So, we don't have an infinite number of theorists.
No, sure.
We don't wish to have an infinite. But it's a logical thing to say. Our working hypothesis in the first generation of this experiment is that it's a Z2 quantum spin liquid. If that's proven false in a different material, then we would move away from this fixed point. But we're just trying to open this window to give new information on quantum spin liquids.
Just my question, is there another Kagome plane above these things or not? We have a sort of Kagome plane sandwich between two.
Sorry, I was being too simplified. So Ian's simulations use many layers, multiple Kagomes.
Yeah, I guess it translates to about 12 layers in my simulation.
So the simulations are approaching a plausible bulk.
So could you mediate these substitutional proffers between two planes?
That's a great question. We have been wondering
Is that
about.
quite scientific?
No, we haven't. We have all been talking about, would it be possible to communicate, quantum mechanical information from one spin to another spin in a coherent way through a quantum spin? That would be cool.
So, is the spin glass on there actually making it more complicated? Or if like I have very isolated spins, and I just measure the spin mass of those very isolated witness spins. Would that be even simpler?
It would be, now that we understand what to do, it would be much easier to do that. But it took us a while to understand. So.
And that would be just easier to obtain then.
Yeah, you'd probably have a single relaxation time for this, for the quantum. Think of it as a cube, right? And you have a bunch of qubits at random locations.
Yeah.
It all have approximately the same relaxation. So from the noise spectrum or from the system. Yeah, from the system. Yeah. So that's a great idea. We just somehow we didn't do it perfectly.
Yes, John.
So if you wanted to be critical and look to that plot, you might say, well, actually, the only diagnostic that you've got is the ordering temperature, T star. And you could have measured that just in a driven measurement where under sufficiently small field conditions, you saw that in the driven measurement. And going to 1 over F is just correlated with forming this spin glass state. So that then raises in one's mind the question, let's suppose you didn't have any spins in an ideal world. Could the noise be a discriminator? If it were possible to cleanly measure the noise of a spin liquid,
yes.
Is there a clear sort of theoretical correlation between the noise spectrum and the nature of that quantum spin liquid, of which there are many kinds?
Yeah, right. So I think it's a question which we have been considering following all these theories. Right? If you read them very carefully, you see that they can distinguish between some different categories of quantum spin liquids, like with and without a Fermi surface, or U1 direct can be distinguished from gaps, for example. Right? So at that level, the question is, the answer is already yes, should be able to do a perfect experiment. Now, the kind of dream experiment I would like to do is, you get a new spin liquid sample, you put it in the machine, you press a button, and when you come back in the morning, you know what happened. That's right. So we're not at that point yet.
Yeah, very simple question. The Kagome monolayer, is it gapped electronically? Is it the metal? Is it an insulator?
So it's all an insulator. It's a high gap insulator, very high. That's why it's an almost perfect quantum spin liquid.
Yeah, Sam.
Yeah, so in this discussion of models, there's two different models as far as I can see, a model of the Kagome layers and then a model of the witness spin.
That's correct.
And as far as I could see, the only input from the Kagome model to the witness spin ones was that it was capped. Because the theoretical model of some exponentially decaying thing.
Yeah, see this number here?
Right.
Sorry, this number here, that's the strength of nearest neighbor interactions.
Okay, but as soon as you're basing something on a strength, then the fact that you've got easing spins in the witness really matters, because this changes things by factors of 2 or 3. I mean, not orders of magnitude, but
yeah, that's perfectly correct. I agree with
that.
I agree with that. But we are not just using one number, right? The map of Jij, which is being used, is using dozens of numbers at a wide range of distances.
Yeah, but then you've got a formula for it, and the only thing that gives a formula of that form is that the excitations are gapped.
Yeah, and the magnitude.
Okay, it is some magnitude. But magnitude, you've got to be careful, because this easing approximation really is going to screw up magnitude.
I completely agree. We did our best on the first try.
Yeah, I don't know. I mean, I'm not complaining, but I just think this is going to be a very difficult way to say what's going on in the Kagome layer, because the only thing that's coming out of it is this huge integral overall spin.
Imagine that there are experimentalists who might not have to use that integral to get the information on the next round of experiments. And so it's our job to find a way forward.
Yeah, no, I mean, really interesting. I'm not complaining, just saying.
Are we done?
I think we're gonna, I'm sure we could go on for another half hour, but I think we're gonna hold it there, and you can talk to Seamus offline after the talk. Thanks very much. Great.
How unique is this?
Now, a very important question, which is, Where is the? And what time should we come back here? Sam, should we come back at 10 to the hour, 10 to 12?
Yeah.
10 to 12. Back here for talk by 10, 10, 9. Okay.
So
Okay, thank you.
And I mean, of course, you can do more careful numerics, but I think they then just took this one.
Yeah.